say we want to find the output y of s. We have three inputs: reference signal, disturbance, and noise. So, the output y of s, you can write as the sum of the individual outputs due to these three input signals. So, the sum of the output due to the reference signal plus the sum of the output from the disturbance plus the output from the noise. And now each of these individual outputs we can write, so individual output, as the transfer function of the block multiplied by the input. So the individual output is the transfer function multiplied by the individual input. So let's look at the output due to the reference signal. We said the transfer function, so you can write it like this, from the reference signal to the output, multiplied by the input, which is the reference signal itself. Okay, so how can we write this transfer function? We can write it as a fraction. And on the numerator, you write what's going on in the forward path. So from the input to the output, this is your forward path. And on the denominator, you write what's going on in the loop. So from this comparator, back to the comparator is your loop. Okay, so for the numerator, what's going on in the forward path? We have two blocks, one for the controller and one for the plant. And since both of these are in series and in Laplace form, we can represent them as a single block, GC, GP. Notice how in between them you have the disturbance signal, but we are only looking at the output due to the reference signal at this point. So you can just ignore anything going in between. So we said GC, GP is on the numerator, and on the denominator for the loop. Since we have a feedback loop, always gonna have to write the value of 1 on the denominator for feedback loops. And what's going on inside the loop? It's the same two blocks we had before that are in series. So just add once again the two blocks that are in series. Okay, and of course multiply by R of S. Next up, we need to find the output due to the disturbance. Once again, you can write this as the transfer function from the disturbance to the output. So from the disturbance to the output, multiplied by the input. So output is transfer function multiplied by input, and the input is the disturbance signal. Okay, so what's the transfer function for the disturbance? Once again, we can write this as a fraction, and on the numerator we write the forward path. So from the disturbance signal to the output, y of s, in the forward path we only have one block, one transfer function GP, so the plant GP. And on the denominator, on the denominator, we write what's going on in the loop. So from this comparator back to this comparator. Since it's a loop, always write the value of 1. And what do we say is going on in between these? Once again, GP, GC. So GP, GC, GC, GP, same thing. So add the GC, GP and multiply by the input. Okay, last one is the output due to the noise signal. This one is a little bit different because I'll tell you later. So once again, the transfer function for the noise to the output multiplied by the input, which is the noise signal. So why is it a little bit different? It has to do with the transfer function for the noise signal. And you can see this one's placed in the loop. So on the numerator, we said we write the forward path. So what's happening in the forward path? From the noise signal to get to the output, this is your forward path. And since our noise signal starts acting somewhere in the loop, in our negative feedback loop, what's going on in our forward path, because we're passing through the negative feedback loop, is minus GC GP. They're in series again. So minus GC GP. And on the for the loop, once again, you write the value of 1 because we're dealing with a loop. And what's going on inside the loop? GC GP. Okay, so you have the total output as the sum of the output due to the reference signal plus the output due to the disturbance and output due to the noise. Each of these individual outputs we wrote as the product of the transfer function and the input signal. Let me times this one by the noise. So that's basically it. But one thing to keep in mind is when you want the output, usually you want most of the output to be due to this reference signal. You don't really want to have much of your output influenced by the disturbance or by the noise signal. So to show this, you want your transfer function due to the reference signal, so this one, to be pretty much 100%. Not very accurate, it's pretty ideal, so this should equal 100%. So you can equate your transfer function to a value of 1. You want to minimize the effect of the disturbance and noise ratio. Ideally speaking, you would want it to be as close to 0 as possible. So the transfer functions due to the disturbance and due to the noise signals, you want to equate them to 0. And